Okay, today we study Cartesian components of a Euclidean vector. Until now, that we we learned that the Newtonian mechanics assumes the space is a Euclidean, three-dimensional Euclidean space. Any position vector in a Euclidean space is conveniently expressed in terms of Cartesian components. A vector, perhaps you might know that this is a mathematical object, but that originates from a displacement that represents the change in the position in space. And vector is a just abstract concept, carbon copy of the abstract mathematical object coming from the displacement. So many of physical observables are vectors because we describe the motion of a particle, the motion of matter, and we assume that particle is enough to approximate the position of matter. So we study the how to describe the displacement, velocity, acceleration, and so on in terms of basis vector. In one dimension, we have a single direction, and vector has a magnitude, both magnitude and direction. We assume that there is a basis called E1 hat. There's a unit vector along the x-axis. And then we multiply a number, so-called real number, to represent any point on this axis. This is the case for the one-dimensional Euclidean space. In two-dimensional Euclidean space, there is another direction that is perpendicular to the original direction. Sure, it doesn't have to be the perpendicular to the original direction. At least it has a tiny component that cannot be described by the original uh, basis. So we have another basis called E2 hat that is perpendicular to that. If it is not the case, if it's not perpendicular, but theta is not zero, E1 hat, E2 hat can be introduced to describe any point in space in two dimensions. But convenience of this orthogonal basis is that there is no overlap between the two components. So in here, this amount can be expressed in terms of this and can also be expressed in terms of parallel component of E2 relative to E1. So this is not convenient. Sometimes it is convenient, but in most cases it is convenient to choose the basis. Basis means inevitable direction that should be accounted to describe a position of a particle. So in two dimensions, we have two basis vectors, and we uh, choose them to be the orthogonal to each other. In three dimensions, we have three independent directions: E1, E2, and E3. All of us are familiar with this kind of basis choice that is called Cartesian because it is coming from the Descartes. The geometry began with the Euclidean idea. However, Descartes is one of the most important person who have introduced these Cartesian components that made us to describe geometry object in the algebraic way. Simple math can be applied to express, for example, a circle. We introduce coordinate system, the two-dimensional coordinate system with x and y axis. Those basis vectors are e1 hat and e2 hat. If we introduce this kind of coordinate system, any point on a circle can be described by two coordinates, x and y. And actually, the position vector is a linear combination of these two basis vectors, and the coefficient of them represents this x comma y. These coordinates are just a component along a basis vector. In physics, as well as mathematics, by making use of Cartesian components, greatly reduce the amount of calculation. So this is very, very important to understand what's going on in the Cartesian coordinate system. All right. What is a vector? I would say vector is a displacement. And with what we study in here is concentrating on the structure of displacement and its algebra. When we write a vector, we use italic letter. It is not Roman. It is italic letter, and sometimes we put an arrow on top of it, or bold-faced. Bold-faced italic letter represents a vector. Vector has a magnitude like a scalar, and as well as the magnitude, vector has its own direction. That's important. This is because vector is an ideal abstract mathematical object coming from the displacement. Displacement, change in position, has the magnitude and direction. This is different from opposite displacement. So vector has the magnitude and direction. We use an arrow to represent the vector, and the length is the magnitude, and the arrow represents the direction of a vector. In the displacement, the starting point and end point, starting point is represented by the tail of the arrow, and the end point is represented by the head of the arrow. If we make use of 2 points of starting point and end point, we usually use this arrow to represent this is tail and this is head. This is starting point and this is end point. How can I determine two vectors are the same or not? We say equivalent. That means A equals B. If two vectors are the same, they must have the same magnitude and they must have the same direction. The same magnitude in different direction can be represented by this kind of example. This is unit circle, and the center is O, the red vector and blue vector. Their magnitudes are the same. However, the directions are different. How can I copy a vector keeping the direction and the magnitude as well? That is translation. Translation of a vector is keeping the direction the same and length the same. If I make a translation, then another carbon copy of a vector of A is produced. You will find that this translation generates a geometric structure called a parallelogram. Each side, opposite sides of a parallelogram has the same length. So the magnitude of the two vectors, these two vectors are the same, and these two vectors are the same. Sure, the magnitudes are the same, but direction may not be the same, so you have to choose the same direction. So this kind of transformation is called a translation. So translation and invariance of the vector is quite useful to define addition. Suppose that we have two vectors. I have a vector C here. What can I do? Translating this C to there, then you can connect head and tail of two vectors. The addition of two vectors is defined by the connecting the tail and head of these two. So in such a way, we can define A plus C. So vector addition is also can be defined by using translational operation. Here, this is an explicit example. I connect the head and tail of two series of vector and just connect the tail of the first one and head of the last one to find A plus B. But another combination is also allowed. If I translate this B over there, B, and translate A over there, I have A. So in this case, we have a B plus A. It is evident from this figure of parallelogram that A plus B is exactly the same as a B plus A. This is not mathematics. Not mathematics teaches us nature. The space structure of nature has its structure, its property. Basic natural property of displacement is commutative. We can extend this idea to add the three vectors, but that is for the associative law. So A, B, and C. If I combine three of them, I would get A plus B plus C. The sum of these three vectors can be computed A plus B, C, directly connecting the tail of the first one and the head of the last one. Mathematicians like to more straightforward way. This just A plus B first and then C. So because they they usually stick to the basic rules. So they assume that addition of only two vectors are known, and they want to extend it to many ones. So physicists will find the answer directly, whether it is mathematically well defined or not. But later, one can find an easy way to find out a plus b first, and then add the c last. Either way, we can add b plus c and then add a later. So in this case, a plus b and then c and a plus b plus c, they are the same. So mathematicians say it is associative law. However, if you look at this figure, this kind of complicated step to verify this associative law is a little bit stupid. It's just, it is too evident. It is explicit that three, sum of the three vectors is always well defined for any combination of order of operation. So in summary, vector addition is commutative and vector addition is associative. This is the simplest example of a vector operation, but as you can see in the straight line, if I introduce a unit vector E1, I can find another vector by multiplying a number. Multiplying a number, then I can elongate the vector. If I multiply negative value, it doesn't have to be minus x, it is just anyway negative number, for example minus 2e, then this one becomes opposite direction, it changes the magnitude. So we have a vector and a number multiplied to a vector, then magnitude of x is multiplied to magnitude of a to find the magnitude of this resultant vector. So if x equals 0, the length becomes 0. If it's either if it's non-zero, changes the length. So magnitude is greater than 1, then the length of the vector is increasing. Absolute value is less than 1, the length decreases. So if you multiply 0 to any vector, I would get a vector that does not have any direction and does not have any length. Because I do not have any length, there is no way to describe the direction. Only if I have a length, I can choose any direction, right? But a point, it does not have any magnitude, so there is no way to describe direction. That kind of vector is called null vector or zero vector. No magnitude, if I add a vector to null vector, then this one is just A. So mathematicians say A plus 0 is A, 0 plus A equals A. It's so evident. I did not move at all. So the original vector should be the same as the sum with the 0. So the resultant vector is invariant. Resultant vector is just the same as the original vector. That's the reason why 0 is called additive identity. All right. If I know the additive identity, I'd like to find an element that produced additive identity. So cancel the operation. I'd like to cancel this displacement by adding something. Cancel means no effect. What should I do? The answer is minus a. Minus a can be obtained by multiplying minus 1 here. So magnitude is the same, but direction is opposite. So if I make a displacement, and I'd like to cancel this displacement, this is a and this is minus a. The result is 0. So this is additive identity, and this is called additive inverse. All right. So, review. If I multiply a scalar to a vector, then the magnitude will be the magnitude of the original vector multiplied by the magnitude, the absolute value of the real number. And the distributive law works for the vector addition and multiply. When we multiply a number, that can be decomposed into sum of two numbers. And if we multiply a vector, I can divide it into two pieces as the sum of two vectors. That this kind of distributive law works. We have just studied additive identity and the additive inverse of vector summation. The next step is to study scalar product. Scalar product is a very important operation of two vectors. I have two vectors. If they are collinear, if they are collinear, it is either parallel or anti-parallel. If they are parallel, the scalar product is defined by just product of magnitude. If they are anti-parallel, the scalar product is defined by minus product of the magnitudes. Here, this is exactly the same as magnitude, here opposite to the magnitude. In general, if the two vectors have some angle, here you have noticed that these are projection onto the other. The general idea of a projection of the product onto one another can be expressed as a scalar product B is A dot B parallel. That means B's parallel component relative to A, or A parallel dot B. Here, A parallel means A's component that is parallel to B. Then we can generalize this scalar product in general case that is A magnitude, B magnitude, and cosine theta, where theta is the angle between A and B. Let's say A is here, B is here, and A can be decomposed into two pieces. One is A parallel, that is a parallel to B. The other is A perp, that is a perpendicular component relative to B. So A is a sum of a parallel component and perpendicular component relative to B. If I take the scalar product A dot B, then A parallel dot B plus A perpendicular dot B. A perpendicular component has no component along the b-axis, so we would like to erase this, and we, we can find this way. In a similar manner, B can be decomposed into B parallel plus B perpendicular. That means B A B, and B is decomposed into B parallel O. B parallel, B parallel, and B perpendicular. B parallel means B's component parallel to A, and B perp is B's component perpendicular to A. So in this way, we can define the scalar product. Then, simplest example is A scalar product with itself. That is, because A is always a parallel to itself, it is A magnitude. Sure, cosine 0 equals 1. So it is an absolute value of A squared. Hence, the magnitude of a vector can be expressed as a positive root of A dot A. For simplicity, we use A dot A expressed as A vector square. Once you know the magnitude of a vector, it is straightforward to find the unit vector along that vector, because the magnitude of A is a absolute value. We divide this one by the magnitude. Then it becomes hat. Hat means unit vector parallel to A. So if we make use of this notation, A hat is A vector divided by square root of A squared. Next, we consider Cartesian component. Any vector can be decomposed into sum of x, y, z, w, and so on. There are numerous ways to express a single vector. For example, if I make use of arrow, this is a vector. I can add this for x, y, and z, w, and so on. And at the end of the day, you reach the end point. So what's the best way to describe this vector A? It depends on the problem. But if the problem is not, it has a specific condition, it is in general, it is convenient to separate into perpendicular pieces. If you have a single vector, the most convenient way is to introduce x-axis parallel to A and introduce the unit vector that is just a simple unit vector parallel to A. This is the simplistic case. If I do not want to this choice, the simplest choice for the one-dimensional case, perhaps I have A, but I can introduce an x-axis along this line. Then I am not able to express this vector A in terms of a single vector because the unit vector E1 hat is not parallel to A. Then I have to find the component of A that is perpendicular to the x-axis. So I need to introduce y-axis. Then I would have a different unit vector. And E1 dot E2 equals 0. Sure, for simplicity, I want to choose E1 squared and E2 squared to be 1, to have a unit vector. Then, what I need to do is expand this vector A in terms of E1 and E2. Then, the coefficient is called AX and AY. These are called coefficients and components. X component, Y component. When we say there is a component, then component is a coefficient of a basis vector. Basis vector is a linearly independent vector. Then linearly independent means they cannot be expressed, E1 cannot be expressed in terms of E2. Absolutely not, because they are orthogonal. E1, E2 cannot be expressed as E2. If we are in a three-dimensional space, we need to have E3, but E3 must not be on the same plane where E1 and E2 are placed. So such a vector that cannot be expressed in terms of any other vectors, so they are called bases. And there are many choices of bases, but simplest choice is the orthogonal set, that all of the elements are making right angle. In that case, the scalar product among them is always vanishing except for the scalar product of itself. This coordinate system is called the Cartesian coordinate. The basis E1, E2, E3, these, all of them, square is 1, and scalar product between any two different x's equals 0. That is called the Cartesian coordinate, and their coefficient to express a vector is called the coordinate or component. Coordinate is used for the position vector. Component, a Cartesian component of a position vector is called the coordinate, and in general, the velocity, acceleration, force, any kind of whatever vector, the coefficient is called component instead of coordinate. So in one dimension, vector A expressed as a single coordinate or a single component and single basis vector. A vector is in two dimensions. We need two basis vectors. They are orthogonal, and those coefficients are x coordinate and y coordinate. If you are living in the three-dimensional space, the vector A can in general be expressed in terms of a linear combination of E1, E2, and E3, and the coefficients are components, x component, y component, and z component. In any case, Cartesian coordinate basis of Cartesian coordinates itself, the scalar product of itself should be 1 because the length is normalized to be 1 for simplicity of calculation, and all of the three axes must be orthogonal to each other because length is 1, and cosine 90 degrees. In a similar manner, E2 dot E3 and E3 dot E1 is also 0. So if I combine everything all together, I find EI dot EJ should be either 1 for I equals J and or 0 for I is not equals to J. So this is a simple relationship for the basis vector, three basis vector for the Cartesian coordinate system. And these numbers are called Kronecker delta. Kronecker delta is a very simple number. Subscript I and J are the same, then the value is unity. Subscript I and J are different, then the value is 0. A cube of unit side in three-dimensional Euclidean space, these edges represents the x-axis, y-axis, and z-axis. And this length is unit length. Then I would say sometimes I have, this is E1 hat, J hat, this is E2 hat, K hat equals E3 hat. This one is identical to this one is identical to this, and this one is identical to this. What can I do if I want to find out the component of a vector? Then I would use a very simple relation, EI hat dot EJ hat equals delta IJ. This is 1 for I equals J, and this is 0 for I is not equals J. A vector dot E1 hat, what it is? It should be E1, A2, E2, and A3, E3. So this should be expanded in this way. I take the scalar product of E1 hat. However, in these three terms, this guy and this guy vanishes because E2 hat dot E1 hat equals E3 hat dot E1 hat equals 0. Therefore, is A1 E1 hat dot E1 hat. Same thing, A equals 1. A1 times 1. So this is A1. In this manner, x component a1 means a x, a2 means a y, a3 means a z. So every Cartesian coordinate can be obtained by taking the scalar product with the unit vector. Here, I use the subscript that runs from 1 to 3. We call this one to be the vector index. Usually, vector index is written in an italic letter, I, J, K, and so on. Let us consider the Pythagoras theorem. This Pythagoras theorem is for the right triangle. This side is x, this side y. Then hypotenuse is x squared plus y squared square root. This is also true for any vector in the Cartesian coordinate system. In Cartesian coordinate system, a vector can be decomposed into ax, I, ay, j. That is a1, e1 hat, a2, e2 hat. They are orthogonal to each other. They are perpendicular to each other. So this side, horizontal side is a1, and vertical side is a2. And this is a right triangle. Therefore, the magnitude is y1 squared plus a2 squared. Okay? So, a vector is a1, e1 hat, a2, e2 hat. I can pull out the magnitude, a vector, and a vector magnitude is the square root of a1 plus a2 squared. And this is a1 over a vector e1, a2 over a e2. We know that the sum of these two, square root a1 over a magnitude squared, a2 over a magnitude squared equals 1. Very simple parameterization can be found as cosine squared theta plus sine squared theta. Right? It's always 1. So a1 over a absolute value is cosine, a2 over a absolute value is a sine. Therefore, we can express any vector a as a product of a and a hat should be of the form cosine theta e1 hat sine theta e2 hat, where theta is the angle between the vector a and the x-axis. In 3 dimensions, we can apply Pythagoras theorem twice. The xy plane, xy component, we can obtain the x component, y component, and we have the z component still. This one is making a right angle, and finally we obtain square root ax squared ay squared plus az squared, that is the square root of ax squared plus ay squared plus az squared. So magnitude of vector in terms of Cartesian coordinate system is quite compact. This compact relation is due to the orthogonality. EI hat and EJ hat equals delta IJ. For example, A dot B can also be computed. It's A1, E1 hat, A2, E2 hat, A3, E3 hat. Same thing. The answer is A1 squared E1 dot E1. A1, A2, E1 dot E2. A1, A3, E1 dot E3 plus A2, A1, E2 dot E1, A2 squared E2 dot E2, A3, A2, A3, E2 dot E3. Last line, A3, A1, E3, E1, A3, A2, E3, E2. A3 squared E3 dot E3. There are 9 terms, however, everything disappeared because EI dot EJ equals 0 if I is not equals to J. So the only surviving terms are these 3, and these 3 has E1 squared, E2 squared, hat hat, E3 squared are all 1. So finally, we find the scalar product in terms of Cartesian coordinate. This is true only in the Cartesian coordinate. A1, B1, A2, B2, and A3, B3. If we substitute B equals A, then we obtain A1 squared, A2 squared, and A3 squared. So even proving the Cartesian coordinate, proving the Pythagorean theorem is very, very simple. First of all, we use the Pythagoras theorem here. However, in the expansion, we have never made use of Pythagoras theorem. That means this is the proof for the Pythagoras theorem in 3 dimensions. All of these coming from the orthogonality of the unit vectors of the Cartesian coordinate system. So Cartesian coordinate system is a very, very simple. So you have to express many thanks to Descartes for the Cartesian coordinate system. Now we consider matrix representation and transpose. This is just straightforward application of Cartesian coordinate system. So it is very convenient to write the components only, though we expressed the Cartesian coordinate in the Cartesian coordinates. A scalar product was A1, B1, A2, B2, and A3, B3. We have abbreviation for this expression. It takes a long time, so it, it is a little bit awkward to see. So it is convenient to write it as A dot B style. So just put the components of A as a row. This is called the row vector. And scalar product is to the column vector, B1, B2, and B3. And we define this expression. This is an operation of the matrices, and this is to describe the scalar product. So remember, this is developed to express the scalar product in terms of Cartesian coordinates. If you learn mathematics, they define so many things. So it is very difficult to memorize for the first time. But in physics, we are teaching an absolutely different way. Matrix is developed for simple computation of Cartesian coordinates. That's it. So simple Cartesian coordinate expression for the scalar product is we develop this expression, list the numbers of Cartesian coordinates in row and column. And if you write this, this is to represent the scalar product. So how it works? The first element, multiply. The second element, multiply. The third one, multiply. And then add them up. Why? Why? This is because the Cartesian coordinate system gives the scalar product as this form. That's it. There is no reason. When you square a vector, you have a list of Cartesian components, the same thing. So first, multiply, second, multiply, third, multiply, and add them up. That's one. That is A1 squared plus A2 squared plus A3 squared. That's it. You don't have to look for any mathematics book for how the matrix multiplication is defined. It is just came from the scalar product of Euclidean vectors expressed in terms of Cartesian coordinates. That's it. Let's go a little bit further. We define a single number by a multiplication of two vectors. One is row vector, the other is a column vector for convenience. What about the list of rows, the list of columns? You can do the same job for single row and single column. To do that, it is convenient to develop, make a new notation. For example, I have a vector A. Sometimes I can write it down on a row style. But if I want to make use of the matrix multiplication form to describe the scalar product, I need to write it a single vector as a row vector, and the other vector should be stand up. How can I stand up? How can I stand this one up? This operation is called transpose. Make a row to a column. A1, A2, A3. All right. So this is transpose. In opposite way, A1, A2, A3 column, transpose, I transform this column as a row. This is transpose. So if I take the transpose, every row becomes every column. This first row becomes a first column, second row becomes a second column, and the last row becomes the last column. That's simple. So this abbreviation for this operation is very useful to define the scalar product. And if you have a list of scalar products, you have the multiplication of a matrix. And the numbers, listed numbers with many rows, as m rows and n columns that we call m times n matrix. Just forget about anything. Matrix represents the Cartesian components. That's it. Matrix multiplication. Matrix multiplication is basically multiplication and of a row and column. They originate from the scalar product A dot B. And matrix is just matrix representation, realization of what? Cartesian components, A1, A2, A3, and B1, B2, B3. That's it. And the result is just a single number. Okay, what happens if I have an identity matrix? This is identity matrix. Complicated, but everything is zero except for the diagonal elements are one. I multiply a row vector and column vector. What's the answer? The answer is, if I multiply this one in here, the row is still A1, A2, A3. Column is B1, B2, B3. So it is A1, B1, A2, B2, and A3, B3. So in the multiplication, this kind of very simple matrix is inserted. The result doesn't change at all. So this is a identity matrix. So there is a multiplicative identity. You can do an exercise, what you have learned. So a vector can be always be decomposed into parallel to a vector and perpendicular to a vector. So parallel component is always expressed in this way, and perpendicular component can be obtained by subtracting the parallel component from the original vector. This kind of way of finding unit vectors, after you obtain this, you just divide this one by its own magnitude. You will find the unit vector of Cartesian coordinates and the other Cartesian coordinate basis vector. This is called the Gram-Schmidt orthogonalization. We will study further later when we study the rotation. Right? This is a circle. You know, the middle school students know that this angle is right angle with a very complicated way of applying the Euclidean way of proving geometry object. But why don't you follow the Descartes' way? Then the algebraic geometry gives a very simple way to prove that this is the right angle. As a self-test, you can study this one. We learned that this one is identity matrix. We have a simpler, perhaps the simplest matrix. Everything is zero except for a single element. But this matrix is a very interesting matrix. If you multiply A1, A2, A3 to in here, the answer is A1, 0, 0. This one, if you write it as a vector form, it is just first Cartesian component survives and the other two vanish. This is the reason why this one is called the projection operator along or onto E1. In a similar manner, in the middle and the last element, these two are projection operator onto E2, projection operator onto E3. Interestingly, some of this is one-on-one. That is identity matrix. So this is a multiplicative identity of the 3 by 3 matrix. At the end, we can apply what you have learned today to express the spherical polar coordinate. Spherical polar coordinates are very useful for the positioning of a point on a sphere. First, our surface of the Earth is a sphere, and we have longitude and latitude and radius. Because we are on the surface, so radius is fixed, but we have latitude and longitude to represent the angle or position. And usually latitudes are measured from the equator, but in here, spherical polar coordinates measure the polar angle theta from the north. So it's a z-axis, positive z-axis. And longitude is measured from the Greenwich Observatory. And we measure in this way phi, that is azimuthal angle. We can repeat the use of Pythagoras theorem twice. You end up with the new coordinate system called radius, polar angle, and azimuthal angle. And this is the relationship between the Cartesian coordinates and polar coordinates. Okay, that's it for today.